Hello, am I audible? Hello,
Yeah, good evening, sir.
hello, good evening. Good evening and
Good evening,
welcome
sir.
to this session for the NPTEL course Advanced Thermodynamics and Combustion. This is our fifth session, and in this session, we will be discussing what was covered in week 5. In week 5, mostly we discussed thermodynamic properties and their relations. Okay, so we will continue our discussion on that. Okay, so in previous session also we discussed uh, few concepts related to these thermodynamic properties and their relations, right? So I will quickly go through what we discussed in the previous session. In previous session, we discussed what is meant when we say something, some quantity is a property. We discussed that properties are point functions. They are exact differentials. They have exact differentials. They are independent of path, right? All these things. We discussed what is the meaning of exact differential, and if something has an exact differential, then what is the condition that it should satisfy? Okay. We applied that condition of exactness on various quantities, right? We defined these Helmholtz and Gibbs functions and applied the condition of exactness, and we got several equations, right? And those equations we call Maxwell equations, right? We also discussed that several properties are measurable, which can be directly measured, like temperature, pressure, and volume. And certain quantities, they are not directly measurable, but they can be calculated from the measurable quantities, or at least they can be calculated indirectly from measurable quantities. There are certain coefficient, like coefficient of like specific heat at constant volume and constant pressure, coefficient of isothermal compressibility, isothermal expansion coefficient, and their ratios, right? All these things we discussed. Right? We solved some problems, and we also discussed a new mathematical tool called Jacobians, and we did the whole discussion in terms of Jacobians as well. And we found that Jacobians, they are very elegant method to write all these complex partial differential notations in very compact form, right? And also the Maxwell equations, four Maxwell equations, they are just condensed to one single equation. And from that single equation, that is T comma S is equal to P comma V, all the equations can be derived. We also discussed a like sort of algorithm. What should we do if we want to, proceed any question related to these properties, right? So all that discussion we did in the last session. We also tried to do some, examples. We discussed Joule-Thomson coefficient, right? Mayer's relation. I think we just left and asked you to try to prove it yourself using the Maxwell equation, and I hope you must have been able to do that. We also discussed this Clapeyron equation, right? So probably we can start our discussion from here itself, the Clapeyron equation. Okay, so if you have any doubt in the previous session, that you can ask, or we can just continue our discussion from here itself. Have you any doubt in the previous session? Hello?
We'll continue, sir. We can continue. Yeah, we'll
Okay.
continue.
So we will continue with the Clapeyron equation. So I hope you already know that, but a little bit of discussion that will like a revision. Okay. Actually, it is an important equation, Clapeyron equation, because it is related to phase change, and this force is related to combustion. And in combustion, we are frequently encountering with the phase change, because you have a fuel, you are spraying that fuel, you get several droplets, and those droplets, undergo evaporation. So that is a phase change process, right? So this phase change process is very important. So this Clapeyron equation becomes automatically important for the phase change processes. Okay. So in the basic thermodynamic course, you might have studied that during phase change, actually phase change happens at constant pressure and constant temperature. I mean, if you fix the temperature, then if you fix the temperature, okay, then the pressure at which phase change process will take place, that is automatically fixed. Okay, and also the vice versa. If you fix the pressure, then the temperature at which phase change process will take place, that temperature is automatically fixed, right? So in our daily life, the pressure is fixed. How? Because it is fixed by atmospheric pressure. Okay, so the phase change temperatures, they are automatically fixed, right? For example, the phase change of water from solid to liquid, melting of water, that if that is taking place at atmospheric pressure, then temperature is automatically fixed, right? 0 degrees Celsius. Similarly, the boiling, the phase change from liquid to vapor, if that is happening at a fixed pressure, 1 atmospheric pressure, then temperature is automatically fixed. If you change this particular pressure, then the temperature at which water will boil, that temperature will change, right? For example, if you go to mountains, then at mountains the pressure is usually less than 1 atmospheric pressure. Okay, so the boiling temperature, that also drops. Okay, so many times it is asked like that, uh, the food will be cooked, is early, or it will take more time for cooking if we are doing cooking at mountains as compared to when we are doing at, at plain. So we know that at mountains, if you are cooking the food, it will take more time. Why it will take more time? For example, you are making, let us say dal, आप कुछ भी पका रहे हैं, आलू उबाल रहे हैं, you are cooking potatoes, then cooking will take longer time or less time if you are doing cooking at mountains. And why so? Hello? If you are cooking potatoes at, let us say some plain area, let us say in Kanpur, and it takes some time t in Kanpur, and if you are cooking potato at, at some mountainous area, okay, then it takes some time t mountain, then t mountain is usually larger than the Kanpur or any plain area. So why so?
To the potato will be lesser because water will be taking more enthalpy and vaporizing.
Huh?
So that because of the latent enthalpy, heat of enthalpy, less heat only will be going to the potato maybe.
Latent heat, okay, if you can assume the latent heat to be constant at Kanpur or at the mountain, then what will happen? What is latent heat? Heat is the, amount of heat that it takes for, water to change its phase from liquid to vapor. Right. So I mean, even if you assume that heat is constant, then I think you might have, encountered this question quite a few times, right? So it is very, popular question that is often asked in context of the relation of boiling temperature to, pressure, atmospheric pressure. So I mean, what is the difference at mountain and at Kanpur?
Pressure is higher. Pressure may be higher at As we go up, pressure is reducing and temperature is reducing.
Temperature is reducing, atmospheric temperature is reducing. Okay, fine.
I mean, the boiling temperature is also reducing.
Boiling temperature also reduced, right? So if the boiling temperature is reduced, then water should boil more easily, right?
Yes, yes.
But our purpose is not to boil the water. Our purpose is to cook the food, right? So the heat is transferred from water to potato, okay? And the amount of heat that is being transferred from water to potato, that will depend on the temperature difference between temperature of potato and temperature of water, right? So the maximum is okay. So if you increase the temperature of water, then more heat will be transferred to potato. If you can increase that temperature of water more and more, then more and more heat will be transferred to the potatoes per unit time, right? So heat transfer rate will be increased, but there is a limit on the temperature of water that you can keep, right? So if you try to increase the temperature of water, then you can increase the temperature of water only up to its boiling temperature, right? So for example, in Kanpur, let us assume the pressure is approximately 1 bar or 1 atmospheric pressure, and boiling temperature is, let us say, 100 degrees Celsius. Then you cannot increase the temperature beyond 100 degrees Celsius. Okay, so the maximum temperature you can keep your water is at 100 degrees Celsius, right? So if you are keeping your water at 90 degrees Celsius, then heat transfer will be less. But if you are keeping your water at 100 degrees Celsius, then then heat transfer rate will be more, right? But if you go to the mountains, then the maximum temperature at which you can keep your water, it is reduced, right? Because the boiling temperature is reduced. Okay, so maybe the boiling temperature is reduced to, let us say, 80 degrees or 90 degrees. Then you cannot go beyond 90 degrees or 80 degrees. Okay, so food will be cooked more quickly if you are keeping your water at higher temperature, right? But since you are going on the mountain where pressure is less, atmospheric pressure is less, so the boiling temperature is reduced. So you cannot keep your water at higher temperature beyond the boiling point temperature. So the rate of heat transfer will be reduced and the time taken for cooking the food will be more. Okay. And so the story, I mean, the crux is that this temperature at which the boiling will take place is dependent on pressure, and pressure at which boiling will take place is dependent on, you know, pressure is dependent on pressure, pressure is dependent on temperature, and temperature is dependent on pressure. Okay, and same goes for all other type of phase changes like sublimation or melting. Okay, so this pressure at which phase change is taking place, that we call saturation pressure, and temperature at which this phase change takes place, that we call saturation temperature. Okay, and they are the function of each other. Okay, if we ask how this saturation pressure changes with saturation temperature, that we want to calculate. Okay, so that is the purpose of this Caliparion equation. Okay, so we want to calculate this quantity. Okay, and we how do we proceed? We will use a Maxwell equation. Now, which Maxwell equation? If we see carefully this particular term dp by dt, then which Maxwell equation we will use? Okay, so first of all, let us write the Maxwell equation in our uh, Jacobian form. What was the Maxwell equation in the Jacobian form? It was v comma p is equal to s comma t. Correct? Okay, so we'll proceed. I mean, start with the Maxwell equation itself.
Sir, excuse me, sir.
Yes.
Sir, is it okay for you maybe to take 2 minutes to say that Jacobian, because I was not there in the last class.
Okay. So maybe I can quickly discuss Jacobian, or I can just write the particular Maxwell equation directly. So there is a Maxwell equation d del P by del T at constant volume is equal to del S by del V at constant temperature. Is it one of the Maxwell equation? Hello?
Yes, sir.
You know
Yes,
the
yes.
okay.
Sir, Maxwell equation I know, exactness I know, but the quick, you told a quick way to remember. No, that only was.
Which one? Hello? Max, your voice was not, I mean, proper. I could hear that you are saying that Maxwell equation you know, but the latter part of your sentence I couldn't
Sir,
hear.
sir, Maxwell equations I know. Only thing is, you told a way to remember it fast. No, that I am not sure. I don't know that.
Okay, actually, in the lectures there were discussed some square or some square thermodynamic square something like that, right? But instead of using that, I discussed a method called Jacobian method. Okay, so maybe I can take few minutes to discuss that. Okay, so I have already uploaded that. I mean, yeah, last session on YouTube, so you can watch that. But just for this particular thing, I will quickly discuss that. Okay, so Jacobian of an okay, just consider two functions f and g. Okay, and these two functions are x and y. Okay, so f is the function of x and y, and g is also the function of x and y. Okay, fine.
Okay,
You
sir.
have you have studied Jacobian in your mathematics.
I have studied it long back, but okay.
Okay, so you can revise that, but whatever we need that we will discuss here. Okay, so the
Okay.
Jacobian of these two functions f and g, not Jacobian. First, let us say write the Jacobian matrix. Okay, so the Jacobian matrix of these two functions f and g with respect to x and y is written as partial derivative of f with respect to x, partial derivative of f with respect to y, and partial derivative of g with respect to x, and partial derivative of g with respect to y. And I'm assuming that you know the meaning of these partial derivatives, which variable you are keeping constant, with respect to which variable you are differentiating. So that preliminary knowledge you have, that I am assuming. Okay, so if you have doubt in any of those concepts, that can also be discussed here. Okay, have you any doubt in that? I mean, partial derivatives.
No, sir. Partial derivative, I'm okay.
Okay, you are confident. Okay, so this is the Jacobian matrix of these two functions f and g with respect to these variables x and y. Okay, the Jacobian of f and g with respect to x and y is defined as the metric, sorry, the determinant of this matrix. Okay, so the Jacobian, we write the Jacobian like this in these square brackets. Jacobian of f and g with respect to x and y. This is defined as the determinant of this particular matrix. Okay, so if you expand this, then what will we get? We will get the partial derivative of f with respect to x times partial of g with respect to y minus partial derivative of f with respect to y times partial derivative of g with respect to x. Is it okay?
Yeah, sir. Sir, did you share your screen or something? Not able to see.
I am sharing the screen. Can you see I am writing?
I'm not able to see the video, I think.
But I am able to.
I will do one thing. I will just leave and join once again.
Okay, okay. Hello. Is it visible now?
Yes, sir. Now it is visible. Earlier, I was not seeing this.
Okay, okay. Then I think I should go again. Okay, so we started with Clapeyron equation, and we discussed that saturation pressure is dependent on temperature and vice versa. Okay, and we wanted to discuss that how this saturation pressure is dependent on temperature. Okay, we basically wanted to find the dp by dt at the saturation or the phase change during the phase change. Okay, And you said that we should discuss this Jacobians. Then we started like two functions f and g. They are the function of two variables x and y. So f is also the function of x and y, and g is also the function of x and y. The Jacobian matrix J is defined like this particular matrix. If you are able to see now, then in the matrix we have written the partial derivative of f with respect to x, then partial derivative of f with respect to y, then partial derivative of g with respect to x, then partial derivative of g with respect to y. Okay, so this is the Jacobian matrix, and we define the Jacobian of the Jacobian of f and g with respect to x and y as the determinant of this particular Jacobian matrix. Okay, so if you expand this, then you get the partial derivative of f with respect to x times this partial derivative of g with respect to y minus partial derivative of f with respect to y times partial derivative of g with respect to x. Okay, so up to here, I hope everything is clear. So if there is any problem, then we can slow a little
Clear,
bit.
sir. Very clear. That's very clear.
Okay, and you said that you are, I mean, comfortable with these partial derivatives. So I hope that if I use some shorthand notation, then you should be able to comprehend yourself. For example, if I have written partial derivative of f with respect to x, that basically means we are keeping y constant and we are differentiating with respect to x, right? Okay, so even if I have not written y here, then it is automatically understood because it is the function of only two variables. Okay, fine. So this is the definition of the Jacobian, and using this definition, you can get several properties of Jacobians. Okay, so I'm not writing all the properties. It is already there in the previous lecture. You can go through that. You can watch the lecture, and I also uploaded this sheet. Okay, so it is already there on the top. Okay, so if you go to the Google Drive, so it is already there. Okay, sorry. Okay, fine. So there are a few properties of Jacobians, like if two variables are repeated, I mean f comma g by x comma y है ना अभी, then if in place of in place of y, if we keep g, then what will happen? Then it will become partial derivative of f with respect to x times partial derivative of g with respect to partial derivative of g, right? We have replaced y by g, right? Partial derivative of f with respect to g, or let us write y instead of g. No, y we have removed and we are keeping g. Partial derivative of f with respect to g, partial derivative of g with respect to x. Is it okay?
Yeah, okay, sir. Okay.
Then what it will become? It will become then partial derivative of g with respect to g, it is 1. And and what else? And this term is 0, the second term. Okay. Why 0?
Because dou g is coming 2 times. So
What is coming 2 times?
it is coming like dou f by dou g. Then we are taking dou g by dou x.
Mm-hmm.
And it is a function of x only, I think. X and g only.
So initially it was from right. This is 0 because these are independent. Okay. This x and g, they are independent.
Okay.
Okay. So that's why I was initially writing y, because G is function of x and y, so it becomes little more complex and confusing. So instead of replacing y by g, let us replace g by y. Okay. Now it is okay, right? In the definition of Jacobian, let us replace this g by y. So now what will happen? So partial derivative of f with respect to x times partial derivative of g. So in place of g, we will get y. Okay. Minus partial derivative of f with respect to y, and in place of g, we will get y partial derivative of x. Now is it okay? Hello?
Yeah, it is okay, sir. Yeah, that's
Okay. And x and y, we are assuming they are independent. Okay. So if x and y, if they are independent, then partial derivative of any variable with respect to another, it will be 0. Okay.
okay. Okay.
So this term will be 0. So what we are getting, okay, if I am not writing something, for example, if I am writing partial derivative of f with respect to x, then y is constant. Okay. Here x is constant, here x is constant, here y is constant, and so on. Okay. So here partial derivative of f with respect to x, here y is constant. Okay. And partial derivative of y with respect to y, this will become 1. Correct?
Yes, sir. Yes.
Okay. So partial derivative of f with respect to x, keeping y constant, this can be written as f divided by x, and whatever is kept constant, that will come twice, once in numerator and once in denominator, right? Okay, fine.
Yes, sir. Fine.
Okay, so this is one of the properties of Jacobian. So there are several other properties of Jacobians. Okay. Hello.
Okay,
So
sir.
those you can go through by watching the lecture and reading this particular PDF, but this is one of the most useful one. And also one more, like if something is repeated in, let us say, numerator itself. Okay, so f comma f divided by x comma y, this is 0. Okay, so whatever properties you have read for studied for these partial derivatives, all those properties you can write in terms of Jacobian. How? Because you know the definition of Jacobian, so you can express all your partial derivatives in terms of Jacobians. Okay, as simple as that. And if you feel difficulty in Jacobian, then you can always write in terms of partial derivative. But if you want to write partial derivative in terms of Jacobian, that also you can do. Okay, so now let us discuss any of the Maxwell equation. So we start with, let us say, any equation. So which one I should start with? What was the first one? Hello.
Yeah, dou t by dou v at s. Yeah.
Okay, let us start with this one. Okay. We can start with this one. Okay.
Okay, sir.
Du is equal to TdS minus PdV. And we also discussed that this potential, Gibbs energy, Helmholtz, then and internal energy, all these are potentials. Okay. So du is equal to TdS minus PdV. Correct.
Yes, yes.
Okay. Now this is in the form of a differential of internal energy. Okay. Since this u is a point function, so this differential should be the exact differential. Okay. If you use the definition of exactness, then you can write actually the definition was of the exactness was, if you write the differential of particular thing z, and if it is like m dx, m is the function of x and y, comma n dy, then the exactness condition is partial derivative of m with respect to y keeping x constant should be equal to partial derivative of n with respect to x keeping y constant. Okay, so this is the condition of exactness. Okay, if we compare this du exactness, this du differential with this dz differential, and you use the condition for exactness, then you can write partial derivative of t with respect to partial derivative of t with respect to
v
keeping
keeping s constant.
s constant, that should be
Should be
equal
equal
to partial derivative
to
of
p
t
p with
with respect
p
to
with yes,
p with respect to s keeping
keeping v constant.
v constant. Okay, so this is one of the Maxwell equation. Now if we write this Maxwell equation in terms of Jacobian, so how do we write this in terms of Jacobian? Partial derivative of t with respect to v, so t with respect to v. Okay, let us go through this once again. So this was one of the property. Okay, this was one of the property. Partial derivative of z with respect to x keeping y constant, that we can write as z with respect to x, and whatever is kept constant that will come twice in numerator and denominator. Okay, like that. Fine. ये
Okay,
प्रॉपर्टी हमने भी डिस्कस करी थी, राइट? Here
yeah.
this one. So partial derivative of t with respect to v, so t with respect to v, so v नीचे है, keeping s constant. Okay, so s comma s, fine, is equal to, now tell what should I write?
Dou t by dou v. Static constant does it.
No, now this is first term we have written. Okay, the partial derivative of t with respect to v keeping s constant, we have written like t comma s divided by v comma s. Okay, so this is only the first term. Okay,
Okay. Then we should write p comma v.
p and partial with respect to s, so s will be
Yes.
in the denominator. Okay, and keeping v constant, so v will be on the both numerator and denominator. Okay,
Okay.
and there was one more property of Jacobian, that f comma g x comma y. Okay, so if you change the order of any one variable, then you will get one negative sign. Okay, so if you change the order of x and y, okay, y comma x if you are writing, then you will get one negative sign. Okay, similarly if you change the order of g and f, g comma f, and you are keeping y comma x, so one more negative sign will come, and both negative sign will cancel out each other. Okay, so this is one of the property of Jacobian that you can prove using the definition of Jacobians. Okay, fine.
Fine, sir. Fine. Because of the
Okay.
determinant, it will come like that. Yeah.
It because of the determinant, it will come like that. So t comma s, or let us change the sign of, I mean the s comma t and s comma v. Okay, the first term we have just changed the order of both numerator and denominator. Then p comma y v and s comma v. Okay. Hello. Is it okay?
Okay, sir. Okay. Yeah, it is okay. Yeah.
Now you can remove both s comma v on the both sides. So what you are left with is s comma t is equal to p comma v. Okay, so the Maxwell equation becomes like this. Okay, so the Maxwell equation which you started with, this Maxwell equation is reduced to this equation, and you had many Maxwell equations, 4 Maxwell equations, right? But all those 4 Maxwell equations can be written,
Sir,
can be
sir,
reduced
one
to
dot, sir, this is sir,
Mhm.
s comma t equals p comma v. That how we will write? Is it like dou s by dou t? How we will write that?
See, It is like how we defined the Jacobian. We defined the Jacobian of f comma g with respect to x comma y. Okay, fine.
Okay. Okay.
Or if you write like partial derivative of anything, partial derivative of z with respect to partial derivative of x. Okay, so it has some
Okay.
meaning. Partial derivative of x with respect to partial derivative of partial derivative of z with respect to x. It has some meaning. But if you simply write del z, then it does not have any proper meaning. Okay, fine. You should have something in a denominator. Okay, so here also you should have something in a denominator. Okay, so here where I am saying that this is the Maxwell equation. So you can interpret it in some way, but to be correct mathematically, you should have something in denominator. Okay.
Okay, sir. Yeah.
Okay, so it is like derivative, but you are not writing the derivative with respect to what. Okay, so it should have something in denominator, but it is up to you what you want to keep in the denominator. Okay,
Okay.
of course it has some meaning. Of course it has some meaning. For example, if you are writing dz by dx, then if you write dz, then you can interpret dz in some way. Okay,
Okay.
but you should have something in denominator, then you will say that it is a derivative of something with respect to something. Okay, so you should have something in denominator. Okay, but you can write it like that. Okay,
Okay, sir. So you are telling I should write some property which is repeating, like ST. If I am writing, I can write like something like HT or something, or
you can, yes, like currently I am just treating that as an algebraic variable. This whole thing I am treating like an algebraic variable. Okay, so I'm not going in the very mathematical terms, what is correct, what is not correct. Okay, so you can divide it by any two same things. Okay, so whatever you are keeping on the left hand side, the same thing if you are keeping on the y another side, then it will be correct. Okay, so if you write u comma v, I don't know what the v comma v are, or you can write like x comma y, x comma y. Okay, so now it is making some sense. Okay, now it is making some sense.
yeah.
So there should be something in denominator, but we are not writing that. Okay, so what I should write in denominator, that I will choose as per my requirement, as per the context. Okay, but the
Yeah.
point
Okay.
that I am trying to make right now is that all the Maxwell equations can be written like that. Okay,
Okay.
okay. So this particular Maxwell equation we have already written. So we started with du is equal to TdS minus PdV. Now let us write another Maxwell equation that will start with dH is equal to TdS plus PdP. Correct?
Yeah.
Is it correct or not? If we start
Yeah.
with
It
the
is
wrong
correct.
equation,
No, it is correct
okay.
only. Yeah.
Okay. So if we write the exactness, so what will we get? We will get partial derivative of t with respect to p at constant s. It should be equal to partial derivative of v with respect to partial derivative of with respect to s at constant p. Is it okay?
Okay. Yeah, it
Or
is
we
okay.
made hmm, is it
It's
okay?
okay. Hmm.
If you want to write in the Jacobian, then t by p, and you are keeping s constant. This should be equal to
V S
p s
S
p
P P.
constant. Okay. So again,
Okay.
just change the order. So s comma t and s comma p. This will be equal to this thing. Okay.
Okay.
And what you get, you just remove the s comma p from both sides. You are finally get s comma t is equal to v comma p. Okay, so every time, so if you start with any of that equation, you will always get this particular form, s comma t is equal to v comma p. Okay,
Okay.
so this is the Maxwell equation. You can check with the remaining two equations. You will get that Maxwell equations are finally reduced to this particular form. Okay, so this, you instead of remembering all those four equations, you can remember just one, this only this one. Okay,
Okay.
and
But
instead of making
just
that
above,
square, huh?
Just above, can you just go up, sir? Just one doubt. Last page. Okay, here we are written ST equals PV, no?
ST is equal to PV, huh?
Here we are writing ST equal VP. Okay, that is okay only. Okay, we can change it.
No. You cannot change the order. So there should be some mistake. So there will be some negative sign somewhere. Okay.
Okay.
You cannot change the order like that. The correct equation is correct one is this one. S comma T is equal to V comma P. So there should be some mistake in this one.
Okay, maybe the equation may be wrong. First time,
We see, we missed a negative sign here, right? It is minus P. Okay. So at very beginning, okay. So there will be one negative sign. There will be one negative sign. There will be one negative sign, and now you'll have to change the order. Okay. So S comma T, this should be equal to V comma P. Okay. The order matters here. Okay.
Okay.
Because of the determinant, right?
Okay. Can I write like T comma S equals P comma V? That way can I write?
T comma S is equal to P comma V. We are multiplying both sides just by a negative sign, right?
Yeah, because TS and PV are easy to remember, I think.
P,
we always
TS, okay, whatever you want to write. So both are same.
Okay.
Okay. So all the remaining equations will also be reduced to this particular form. So instead of remembering that square, actually I don't remember that square. So sometimes you need to remember where the arrow should go, which side arrow should go, what should come on the corners, what should come on edge. So you can simply remember this one, and it is, backed by mathematics. Okay. So there is some underlying mathematics. So it is not just a memorization technique. It has some, mathematical elegance. Okay. And what is the meaning of Jacobian? Why we use Jacobian? That you have already studied in mathematics, you said long back. And Jacobians are very important. So why they are important? Like, for example, you are working in a particular coordinate system. Mostly we are working in, Cartesian coordinate system, x comma y, right? But sometimes you want to transform the coordinate. Okay, you want to change the variable. So instead of using x and y, you want to use some polar coordinates, r comma theta, right? So whenever you are transforming the coordinate system, then Jacobians come into the picture. Okay.
Okay, sir. Thank you. that was very useful because I am studying advanced fluid mechanics also. There I was struggling with that NS Navier-Stokes equation conversion. Okay, thank you.
Then if you are transforming that Navier-Stokes equation, then you might have encountered that. For example, okay, let me give one example from mathematics. Okay, so you have some function f comma x, some function f in terms of x and y, and you want to integrate this f with respect to dx dy. Okay, you want to integrate that, right? But you know that sometimes integration is, not that easy, and you want to change the variables. Okay, then you write that x, let us assume x is the function of some other variable u comma v, and y is also the function of u comma v. Okay, then can you write simply f x comma y dx dy? Okay, so f can be anything. F can be like a x square plus b y square, or plus like anything. Okay, then and x, then can you write it x, sorry, a, and you are writing x in terms of u and v and keeping the square, something like that. Okay, I mean, you will have the function x in terms of u and v. Okay, you will have this function x in terms of u and v and square of that. Okay, so ultimately you will get the whole equation f in terms of y, right? Isn't it?
Yes.
Plus b, y is also function of u and v, and whatever the function is, you can, transform accordingly. And if you want to write this f in terms of, finally you will get this in terms of u and v. Okay, you will get it in terms of u and v. Okay, fine.
Okay.
Then this dx and dy, they will become du comma dy, but you cannot simply write du times dv. Dx and dv, they will also be transformed, but not to du comma dv. Okay,
Okay.
What extra term will come? That extra term is your Jacobian. Okay.
Okay, sir.
Hmm?
Okay, sir. Okay. So Cartesian dipolar means it may be some 1 by R may come like that, something like that.
Let us take a very simple example. Let's take uh, mm, let us take some function x square plus y square is equal to 1. So what is this? This is a circle. Okay.
Yeah.
This is a circle and you want to calculate the area. How do you calculate the area of this particular circle? You do the integration. Okay.
Yeah, I
Correct.
have to take a small strip and integrate. Yes.
You will integrate and you will get a small elementary area. That elementary area will be dx dy. Then you need to integrate this small elemental area across the whole circle. Okay. So what will be the limits on x? First you are integrating with x. Then what will be the limits on x?
It can be
Let
from
us take x
0.
square plus y square is equal to capital R. Okay. Take any radius.
Yeah.
Hmm.
So 0 to R. Both are
0
0
to
to
R,
R.
not just 0 to R, minus R to plus R, right?
Yeah. 2 times. Yes. Sorry. Yeah.
Hmm.
0 to R.
Minus
Minus
R
R to.
to 2 plus R. And the what will be the limits on y?
Y also will be same.
No,
It's,
then it will become a square. Then if you are keeping like that, then it will become a square, right?
yeah.
Hmm. So if you are integrating with respect to x, then it will be changed. Okay. So y limits should be changed. Y limits will be what? X square plus y square is equal to r square. So y square will
R
be
square.
r square minus x square. So y will be once it will
Under
be
root.
r square minus x square plus, and once it will be r square minus x square minus. Okay. So it will
Yeah.
be from minus r square to x square and plus r square x square. Okay. So now this integration is not that easy. Okay. At least for
Yeah.
me, it is not that easy. Okay.
Yeah. Yes, sir. Yes.
For example, the first term with respect to x, you can easily integrate. Okay, so it will be simply integration of dx, it will be x, and when you will be put the limit, it will become 2r. Okay, the first integration is easy. But the second integration, well, we try to integrate with respect to y. And see, in the limits also, we are having x. Okay, so it is little complex. Okay, it is not very, straightforward. Okay. Now what we can do, we can assume that x and y are the function of something else. Okay, so x, let us say, is the function of r and theta. Similarly, y is the function of r and theta. Okay, so r,
Okay,
let
sir.
us write it as r cos theta, capital R cos theta, and y, let us say it is r sin theta. Okay, so it is satisfying that x square plus y square is equal to r square. Fine, we can write it like that.
Okay.
Correct. R square, देखो यहाँ पे r square छूट गया, r square. Okay, we can do it like that.
Okay.
Hmm? Now
Yeah.
we are trying to integrate what? Trying to integrate dx comma dy. Oh, here it should be some function f. Okay, we actually gave you the example that there should be some function f, but here f is 1. Okay, okay,
Okay.
fine.
Hmm.
So we have taken very simple example. Okay, we are integrating just x dx dy. Okay, f is 1 here, simple. Now we are doing coordinate transformation. So how this function f will be transformed? F is equal to 1, so it will remain 1 only. Okay, so no transformation in f, right? But this x, dx, and dy, it will become dr comma d theta, but there will be one Jacobian. Okay,
Okay.
fine. And what was the limits? Minus r to plus r, and here it was minus r square to something x square. It was like that, r square minus x square, ये minus था, ये plus था. Okay. So how the limits will be transformed? The r square minus x square, if you are writing in terms of r that theta, then it will be r square minus x square क्या है? R cos theta squared. Okay. So this will become, it will become what?
R square sin square theta.
R square sin squared theta. Okay. So the limits will be, one will be only minus r to r, so no change in that because it is already constant. But another one will become minus r square sin square theta, actually under root of it.
Yeah, R
So
sin
minus
theta.
r, minus r sin theta to plus r sin theta. Okay, like that. Now what will be the Jacobian of that? Hello.
Sir, Jack. Okay. Sin square theta.
Jacobian of x comma y with respect to r and theta. Very easy.
Okay. 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 That
So
is x r. Okay.
x is r cos theta. So partial derivative of x with respect to r, it will be only cos theta. Partial derivative of x with respect to theta, it will be minus r sin theta. Partial derivative of y with respect to x, not x, r.
R.
R, it will be what? Y was actually, y was r sin theta, right? So partial derivative of y with respect to r, it will be sin theta. And partial derivative of y with respect to theta, it will be r cos
R
theta.
cos. Yeah.
So it will be partial derivative of x with respect to r. X with respect to r क्या है?
Cos
Cos theta
theta. Yeah.
times
Y and theta.
partial derivative of y with
Y
respect to
theta.
theta,
Theta.
r sin
R
theta,
cos.
r cos theta, sorry,
R cos theta.
r cos theta
R
minus
cos
partial
x
derivative of
theta.
x with respect to theta, so minus r sin theta, so minus minus will become plus times sin theta, right?
Okay. Yeah.
So it will be r cos theta is cos square theta plus r sin square theta. So this Jacobian is actually
R.
r. Okay.
Okay.
So our area becomes the Jacobian, that is r times
Dr d theta.
dr d theta. Okay. And the limits are again simple. R say plus r and minus r sin theta to
Plus R.
plus r sin theta. Okay.
Okay, sir.
Now you can integrate with respect to r first. So it will become r square and you will put the limits. What will be the integration of r?
R square by 2.
R square by 2, right?
Then, yeah, R
R
square.
square by 2, then it is twice, okay?
Yeah, so it will be R square
R square, okay?
into theta.
It is, it was r square by 2 and you are doing it twice, right? So it will be r
Yeah.
square. Now you have to integrate r with respect to theta and
R square.
the limits
R
are
square.
r sin theta, no, r
R
square,
square.
sorry, r square and minus plus r sin theta.
It will be 2 times R sin theta. Correct. No?
It will be
R square into 2 times R sin theta. Correct or not? I don't know.
r is constant. So we are only integrating with respect to theta.
Yeah. So it will be theta only. R square into theta.
R square
And
into
for
theta.
theta, yeah,
But where
theta
the
we had
pi? But from where we will get pi? Okay, let's do it and let us see what meant missing.
Yeah.
So R square, it will come out and it will be reduced to theta minus R sin theta plus R sin theta, and it will be only theta. Okay, so R square and R sin theta twice, right?
Yes.
So we had made some mistake. I don't know what.
Whether theta we have to define, sir.
Theta we have
I
to.
think define. Theta has to be defined from 0 to pi or something.
Ah,
That is.
sorry.
Hmm.
Theta, the
That is
limit
okay.
of theta.
Yeah,
Theta
so
limit
that is
will be
okay, sir.
changed.
Yeah, that I can take up, sir. That is okay. We need not spend the time, I think.
Okay. So finally, we will get this pi R square. Okay.
Yeah. Hmm.
So we have to careful while putting in the limits. The limits of theta, they will be from whatever. Okay.
Okay. Hmm.
So now this particular integration is easy. Okay. So whenever we are transforming the coordinate, then this Jacobian comes into the picture. So if you want to transform your Navier-Stokes equation from Cartesian to any other coordinate system, then these things will come into the picture. Okay. Sometimes we don't
Okay.
explicitly write this Jacobian, but whenever you are doing derivation, then maybe indirectly they are coming into the picture. Okay.
Okay, sir.
Anyways,
Thank you. Thank you. It
okay.
was
So
very useful.
I hope now we have some idea of the Jacobians, and we have idea that all these Maxwell equations can be written in terms of Jacobians. Why? Because see what is happening when we say coordinate x comma y. So what x comma y is telling us? X comma y is telling a particular point in the Cartesian plane. Okay. So x and y both are point function because they are defining the state. They are defining a point. Okay. So in thermodynamics also, when we say that some quantity is a property or some property is a state function or a point function. So basically those properties are actually they are defining the system. They are defining the state. Okay. So to define the state, we need two coordinates only. Okay, for a simple compressible system, at least we need only two quantities. If you have pressure and temperature, then remaining quantities can be calculated. Okay,
Okay.
so we need only two quantities. But if you want to define, you want to do some coordinate transformation. I mean, if you want to go from that set of particular properties to another set of properties, then you are doing a sort of coordinate transformation in thermodynamic sense. Okay, right, in thermodynamic coordinate system, you are doing coordinate transformation if you are changing the properties. Correct.
Yes, yes.
So changing the property is basically changing the coordinate system, coordinate transformation. So that's why this Jacobian come into picture. That's what we are doing in this particular topic, relations among the properties. Okay, we are changing the properties and we are basically transforming the coordinates.
Okay, sir.
Anyways, so what was our objective? Objective was to, okay, here, Clausius, Clapeyron equation. So, so I hope this background is enough for our, proceeding with Clapeyron equation. Okay, so what we wanted to discuss, we want to discuss that how the saturation pressure and temperature are related, and we wanted to calculate this partial derivative of pressure with respect to temperature during the phase change. Okay, this thing. Okay.
Okay, sir.
And we discussed that this we know that to define the state, we need, several thermodynamic, not several, two thermodynamic properties. So pressure will be the function of two properties, like pressure can be the function of temperature and volume, right?
Yes.
But during phase change, we discussed that pressure is only dependent on temperature, and also temperature is only dependent on pressure. Okay, so the pressure is the function of temperature only during phase change. Okay,
Okay, sir.
pressure is function of T and V in general, but during phase change, pressure is the function of only one variable. Let us say pressure. Okay, so we want to know that how this pressure is dependent on temperature at saturation. Okay, so now it is quite intuitive that how, first let us write that our equation V comma P, Maxwell equation, was S comma T, correct? Okay, so
Yes,
how should
yes.
we write? So we want to take the derivative of P with respect to T. Okay, so P with respect to T, right?
Yes.
P with respect to T. So just flip this order. P comma V is equal to S T comma S. Okay, we want to write the derivative of P with respect to T. Okay, so P with respect to T. Okay,
Okay.
now V is already there in the numerator. We can write the same thing in the denominator. Okay,
Okay.
so what it is now? So it is partial derivative of P with respect to T at constant V equal to partial derivative of S with respect to V at constant T, right?
Yeah. Yes. Yeah, that is correct.
So
Yes.
this is one of the Maxwell equations. So that's what I was saying in the beginning.
Okay.
Okay. So which Maxwell equation we want to use, that becomes automatically clear if we write our expression in this particular form. Okay.
Okay.
So we will start with this particular Maxwell equation. Okay. We discussed that during phase change, this pressure is not the function of volume or any other thing. It is only the function of temperature. So this partial derivative can be written simply as the simple derivative. Okay. So this partial derivative is equal to simple derivative during the phase change. Okay.
Okay.
Okay. So now first term is okay. First term, there is no problem. We are having now this second term. Okay. ds by del S by del V at constant temperature. अच्छा, ये PT, this dP by dt is basically the slope of PT lines during phase change. Okay, so if you remember, then these lines look something like this. Okay, correct?
Yes, sir.
This is what? This is our vaporization, and this
Sublimation.
is melting. Hmm? No,
Okay.
this is
Another
no,
one.
this is okay. This is solid. This is vapor. So this
Sublimation.
will be sublimation.
Sublimation. Yeah.
And this is solid, this is liquid, so it should be melting. Okay, so fine. So this PT dP by dt basically means the slope of this particular line. Okay, slope of this line, है ना?
Yeah. Yes.
And the second term del S by del V at constant T. Okay. So at a given temperature, so if you have fixed the temperature, so that means at that particular temperature, the slope is also fixed. Okay. So this thing is constant. dP by dt is constant at this particular point. Okay.
Okay.
This is okay if you fix the temperature. Okay. So this del S by del V, this can be written as this G basically means gaseous phase or the vapor phase, and F means liquid phase, fluid phase. Can we write like this?
So that
It is
how we are writing, because the slope is constant. Why we are writing?
Okay. Actually, the slope is constant dP by dt. It is constant. Okay. So the slope of this particular the slope of as V lines at some temperature, this will also be constant. Okay.
Yes, sir. Yes. Yeah. Now I understood, sir. Yes.
So you can calculate slope using any 2 points. Okay. For
Yes.
example, if the slope is constant, then you can calculate the slope at any 2 points. So you can take S2 minus S1, V2 minus V1. These 2 points can be any two arbitrary point
Yes.
within the saturation zone, within the phase change zone. Okay, because it is constant. So this dP by dt at saturation. So for simplicity, we are writing Sg minus Sf divided by Vg minus Vf. Okay,
Okay.
fine.
Yeah. Fine. Okay.
Now, how to handle this entropy?
Yeah. That is the TDS equation.
Using TDS equation. So dH is equal to TDS minus, plus VdP. Okay.
Yeah.
Again, we are doing everything at constant temperature, at a given temperature. So if the temperature is fixed, then dP is also fixed. So for constant dP, this term will be 0. Okay.
Okay.
So dH is equal to TDS. So ds is equal to dH divided by T, and you can integrate that from where to where? From fluid to gas, let us say fluid to gas. Okay. So this ds, if you integrate, so the limits will be from gas entropy minus fluid entropy. This should be equal to, again, temperature is constant. Okay. Saturation temperature. So it will come out. Okay. T saturation and H of gas minus H of fluid. Okay. And sometimes we write this as HFG. So HFG means the enthalpy of gaseous phase minus enthalpy of fluid phase at the ends. Okay, so you can also say that this is the latent heat of vaporization, right?
Okay.
Okay, so this thing you can put here. So the dP by dt at saturation becomes dg minus df. This is our HGF by T saturation divided by V G minus Vf. Okay.
Okay, sir.
So this is Clapeyron equation.
Okay, sir. Basically, so we are saying at a particular temperature, what is the corresponding latent heat to specific volume change? That is what we are saying, right?
Yes.
Okay. Okay, sir.
Or you can also say that if you know the latent heat at that particular temperature, and if you know the specific volume change at that particular temperature, then what will be the slope of these dp, I mean these pt lines.
Okay, sir.
Okay,
Okay.
so it is up to
Okay.
you how you want to interpret that. Okay.
Okay.
So this is a Clapeyron equation, but there are certain approximations. For example, you can make some approximations. Okay. Hello.
Yes, sir.
So
Yes, I'm listening. Yeah.
at low pressures, you know that a specific volume of gases, it is quite higher as compared to a specific volume of fluids. Okay.
Okay. Okay.
So this Vg minus Vf, this can be approximately equal to Vg only, right?
Yes. Yes.
Because Vf is very small as compared to that. Okay. And
Okay.
at low pressures, you can assume that it is an ideal gas. Okay.
Okay. Okay.
Low temperature, low pressure, high temperature, ideal gas, right? Again, it is an assumption. Okay.
Okay.
At very low pressure, we can assume that this is ideal gas. So this is a special case, okay, not in general. We are assuming that it is ideal gas. So if you assume the ideal gas, then what you can write? You can use ideal gas equation. So ideal gas equations means V is equal to RT by P. Okay.
Okay. Okay.
RT by P. So this Vg minus Vf becomes our RT by P. So this we can substitute in the Clapeyron equation. What was the Clapeyron equation? dP by dt at saturation, this was equal to HFG divided by T and Vg minus Vf. So Vg minus Vf is RT by P. Okay. So this again, this is saturation pressure, saturation temperature, that is understood. Okay. So this is HFG divided by T square P by R, right?
Okay.
If you arrange this thing a little bit, then you can bring P this side, dP by P, and dt on another side. So dt by T square and HFG by R. Okay.
Okay.
And then you can integrate it. This will be integrated to log of P, but there is one term HFG. Okay. So if this HFG, we can consider that it is independent of temperature. Actually, it is dependent of temperature, but if the temperature change is not very high, okay, for small temperature changes, HFG can be considered constant, okay, independent of
Okay.
temperature. So you can take this thing out, okay. Then what will the integration will become? This will become log of P. And if put the limit sum 1 2, then log of P2 by P1, this will be equal to HFG by R. And if you integrate T square, then it will be minus
Minus 1/T.
1 by T. Okay. So it will be
1 by
what?
T1 minus 1 by T2.
T1 by T2 or minus T1 by T2. Okay. So this
Okay.
is this equation under these assumptions. What assumptions? That for small temperature changes, we are assuming that HFG is constant. We have assumed that at low pressure, this is an ideal gas. And we also assume that a specific volume of fluid is very less as compared to a specific volume of the vapor. Okay. So under these assumptions, this Clapeyron equation becomes this. Okay. So this special equation under the special assumptions, this is called Clausius Clapeyron equations. Okay.
Okay.
Okay, so Clapeyron equation was a general equation, but Clapeyron equation is an approximation under certain conditions. Okay.
Okay, sir. So I think for applying this equation, then a T1 and T2 are to be very close, no?
Yeah, exactly right. T1 and T2 should be close. Why? Because we want to. We have assumed that change in enthalpy is negligible. Okay.
Yeah. Okay, that's it. Yeah.
So it depends. So it depends how much enthalpy changes with respect to temperature. Okay. So sometimes even if for large temperature changes, this enthalpy change is not that much. Okay. So when we say that T1 and T2 should be close, then how much close? They should be close enough so that this enthalpy can be assumed constant. Okay.
Okay, sir.
So
Okay.
how much close? So that closeness will depend on the change of enthalpy with respect to temperature.
Okay. But generally, whether it will change too much, roughly, if it.
That we can check. You can check on in the steam tables. Okay.
Okay.
I will show you the steam tables. Okay. There's some. I mean, when we discuss the question, then we will refer to the steam table. Okay. Okay. So I think this
Yeah, this is fine, sir.
discussion
Yes.
is enough on Clapeyron equation. We last session we also discussed a little bit about the Joule-Thomson coefficient, but I think you can read that and you
Yeah,
that is already
that I'm okay. I have gone through the lectures. That was okay. Yeah.
okay. So is there any other doubt in Clapeyron, or we can continue with the questions? We also solved some questions last session.
No, sir. No special questions. Only one doubt I was having. Only I don't know. This we were saying this volumetric that expansion coefficient and the volume, specific volume, they are not very sensitive for liquids and the solids. So one,
Can you please, I mean, repeat?
yeah, the dependence of specific volume and coefficient of expansion
Mhm.
is generally insensitive to pressure for solids and liquids.
Ha.
That okay, physically I understand it, but thermodynamically I could not get to it fully. To the exactness of that statement, that is
Mm. I think if you see the diagrams of those, I mean, specific volumes, then it will become clear, right?
uh,
If you remember, like how specific volume is changing with respect to temperature, then you will get that they are like almost constant.
okay.
So maybe I can show you those diagrams. I don't know where is that. Hmm. I think it should be the pure substance, right? Thermodynamically, if you, I mean, this model, it is very popular, like for solid, liquid, gas, why they are not, volume is not changing for liquid and gases, right?
Okay,
They are
okay.
so closely packed. So this is one way to understand. And if you see that these diagrams, this temperature volume diagram, this temperature volume diagram. So see here. So this is the liquid region, right?
Okay.
So this is the liquid region. So if you change the temperature, so it is approximately a vertical line, Okay.
Okay, sir.
Hmm? It is approximately a vertical line. So here, if you see, this is pressure and specific volume. So see, this is approximately a vertical line, right?
Yes.
And this is just a, model or some example. But if you see the real example, then it will be more vertical. Okay.
Okay.
Here it is like approximately vertical. Hmm?
Okay.
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 Okay. Then we discussed some examples. For example, this example number 5. So I will just read it. An equation of state for a real gas is given by this P is equal to some equation, and it is asking us to find the partial derivative of P with respect to T, keeping V constant, because it is required to evaluate the Maxwell equation. Then it is saying that consider the gas to be at 300 Kelvin and 0.86 meter cube per kg, and the state of gas changes to 302 Kelvin. Okay, by 2 degrees it has changed, and this specific volume has also changed, and it is asking us to estimate the change in pressure of gas. Okay, so you can find that, right?
Okay.
You consider the pressure to be function of temperature or volume. You calculate what will be the dp, and all the things are given. Okay, so for calculating this dp, we will have to differentiate this thing with respect to t and with respect to v. Okay, so the expression is given. You can differentiate with easily, right, with respect to temperature and volume, and you can substitute the values and you will get that, right? And it is asking that compare the result if the gas was ideal gas. Okay, so then p will then it will be p equal to RT by V, right? In that case, also you can calculate. Okay.
Okay.
So question number 6 will, on PV diagram for your substance, the slope of isotherm, the del P by del V is strictly negative on both sides, the single phase region and the two phase region. You have to tell whether it is true or false. It is false, right? Because dP by dV in the phase in the saturation region, it is 0, and it's negative on that side, another side, right? So it was false. On a PT phase diagram, explain why the slope of all isomers constant volume lines passing through two phase region at a specified temperature are equal, allowing the slope to be represented as an ordinary differential dP by d saturation.
Yeah, actually, your V we cannot draw. Only P and T only can be drawn. It's a point, I think.
Right. So pressure is the function of temperature only.
Yes.
So if the temperature is specified, then it is a constant, right?
Yes, sir.
Clapeyron equation evaluates property changes accompanying a phase change. Which of the four fundamental Maxwell equations serve as the direct mathematical starting for driving the Clapeyron equation? So we just did that, right?
Yeah.
This Maxwell equation. Okay. So now we can continue with question number 9. During a phase change process, the fundamental TDS equation dH equal to TDS plus VDP simplify directly to TdH is equal to ds, because the phase transition naturally occurs at constant pressure,
Pressure.
right? So pressure is constant, then second term goes to 0. Question number 10, it is saying that using the simplified TDS framework for a phase change, if the enthalpy of vaporization Hg for saturated water at 100 degrees Celsius is 2257 kilojoule per kg, calculate the corresponding change in the specific enthalpy in kilojoule per kg Kelvin. Again, the same thing, right? dH is
Yeah.
equal to TDS plus VdP, and during the phase change, this thing is constant, so dP is 0. So dH is equal to TDS. So ds is equal to dH by T, and you can integrate that. Okay.
Okay.
So delta S. So delta S will be your delta H by T. T you are assuming constant at a given temperature. If the temperature change is not very high, right? Actually, phase change, during phase change, the temperature constant. Okay. So enthalpy of vaporization. So delta S means basically enthalpy of vaporization means H of gas minus H of fluid divided by T. Simply, similarly, this, right?
Okay.
Or in shortcut, we write like this. Okay.
Okay.
So HFG is given 2257 kilojoule per kg, and temperature is 100 degrees Celsius. You need to convert this in Kelvin. Okay. So you'll get something. You can calculate that. Okay. So what will be the value? 2257 divided by 273 plus 100. 6 point something. Okay.
Okay.
6.05 kilojoule per kg kilo. Okay. Now, in any question, this thing is given. Let us say the latent heat of vaporization is given. HFG is given. But you don't know what will be the change in entropy during the phase change. I mean, SFG is not given. Then do we really need this separately, SFG? We don't need that. If the temperature is given and latent heat of vaporization is given, then we can calculate this. Okay.
Okay.
Like this. For example, if we let us cross check this for any other value. Let us open the steam table. Properties of saturated water. तो कोई भी एक टेम्परेचर पर देखते हैं इसको. For example, at 50 degrees Celsius, the enthalpy of vaporization is 2382. Okay.
Okay.
And we want to calculate the entropy of vaporization. Then what is that? 2382 divided by, at 50 degree 50 degrees Celsius we are checking it. 273. Actually, it is not exactly 273. It is 273.15 something like that. But let us write 273. So we'll get some approximate value. Okay. We are getting 7.37. So 7.37. Okay.
Okay, sir.
So if this particular last column is not given, entropy column is not given, you can calculate this as yourself. Okay. 100 degree we have already done. Let us check at some other temperature. Let us check at 200 degrees Celsius. So for 200 degrees Celsius, this is 1939.8. Okay. So 1939.8 divided by 200 plus 273. Okay.
Okay.
273, sorry. So 4.0 or 4.1. Okay. So approximately that. Okay. Hello.
Yes, sir.
So
Yes,
if
yes.
the entropy change is not given, but the latent heat is given, then also you can calculate the latent this entropy change.
Okay.
Okay. One more thing we had to check. You are saying how this delta, this HFG change with temperature. So
Yes.
at 20 degrees Celsius, it is approximately 2453. Okay. Then at
Okay.
200 degrees Celsius, it is 1939. Okay. So it is decreasing a little bit. Okay. So how much is the
Okay.
decrement? That then I think it will be more clear if you can check some graph, but you can check the graph yourself. अच्छा, इसमें आएगा?
Yeah, but roughly 20% is changing now. That is.
Like, see, from from 20 degrees Celsius, if you are changing it up to 50 degrees Celsius, it is changing from 2453 to 23.82. But for like 20, if you are changing it just from 20 to 25 or 30, then it is not much change, right?
Yes.
It is not much change. So जो ये closeness था ना कि T1 and T2 should be close. So that closeness does not mean it should be in points. It should not be like 20 था पहले. Now it should be 20.001. So not that close. Okay. There can be like change of 1 degree, 2 degree, or like 5 degrees. So still there is not much change. Okay.
Okay.
That depends on how much approximations you want to make. If you want exact, then of course you'll have to use exact data. But okay. So you should check the, I mean, graph, then it will be more clear where it is changing rapidly, where it is changing slowly.
Okay, sir.
Anyway, question number 11, according to Clapeyron equation framework, the change in specific internal energy during vaporization Ug minus Uf can be determined solely from temperature, the change in specific volume, and the enthalpy of vaporization without needing to know the saturation pressure. So Clapeyron equation we know, but it is asking the change in internal energy during the vaporization. So Ug minus Uf. So this we can write as Hg minus Hf minus P. P will be constant, right? During phase change. P Vg minus Vf. This. Okay. And from Clapeyron equation, uh, what it is saying, solely from the temperature and change in specific volume. Okay, change in specific volume is needed. Enthalpy of vaporization. Okay, without needing to know the saturation pressure. But see, we need the saturation pressure. We need the saturation pressure. So we can say it is false, but if the temperature is fixed, then saturation pressure is also fixed, right?
Yes.
But how do we find that saturation pressure? Like, we know that saturation pressure is constant at is fixed at a fixed temperature, but again we need to check the property tables. So in some sense we need to know what is the saturation pressure from the property tables, or we can calculate it somehow if we had some uh, value at a reference point. Okay, so what I mean is, like from Clapeyron equation we know that dp by dt at saturation, this is equal to h Fg, or the latent heat, divided by T saturation TGF. Okay. Okay. So if these things are known, enthalpy is known, temperature is known, VGF is known at all the points. Okay. And the saturation pressure is known at one particular reference point, then we can calculate it, right? Using this particular differentiation, correct? Like if you, am I right? Like if you know x1, y1 at a particular point, okay, and you know dy by dx at all the points, because we know this hfg at all the points, temperature we know all the points, this v all the points we know. It is written in the question that we know these values. Okay, so dy by dx we know at all the points, then we can calculate y at any arbitrary point, right?
Okay.
Hmm?
Okay.
What will be y? You can just integrate this. Okay,
Yes.
so in some sense we know this slope dp by dt in terms of latent heat, temperature, and specific volumes. Okay. But if we know this pressure value at one particular reference point, and if we know these latent heat, temperature, and specific volume at all the points, then somehow we can integrate and we can calculate the saturation pressure at that point, and we can calculate the change in this internal energy. Okay. So in some sense, yes, we do need the value of saturation pressure. Okay. But if we have the value at one particular point, we can calculate. Okay. But we had to tell it is true or false. So yes, in some sense it is false because we need the pressure value, but we can also calculate the pressure value. Okay. So instead of answering it in true or false, uh, this discussion is important. You should understand, right? That we need the pressure value. We can get that pressure value from any reference point or the property tables.
Okay, sir.
Okay, now question number 12. It is saying that slope of fusion curve on APT phase diagram for water is uniquely negative. Using the parameters within the exact Clapeyron equation, physically explain why this occurs and what it implies about the specific volume of ice compared to liquid water. Okay. So we made this PT lines like this for any liquid, right? It was sublimation, it was melting, it was vaporization. But for water, but for water, this line is melting line is something like this, some in this region. Okay.
Yeah. Okay.
Why so? Now we can, it is asking Clapeyron equation, physically explain why this occurs. Okay, so Clapeyron equation क्या है? dp by dt, ये slope why it is negative, this we have to tell. So what is dp by dt from Clapeyron equation? It is latent heat hfg divided by T saturation and V G minus Vf. Okay. So this latent heat of vaporization is positive or negative for water? It is positive, right? We need to give some heat for vaporization. Sorry, it is about melting. Sorry. You need to give some heat to melt the ice, right? So the latent heat of melting, I should use uh, F and S. Okay, so F for fluid, S for solid. Fluid. Okay. Okay. So HFS, it is positive because the latent heat of melting of water is positive, right? You need to give some heat to melt the ice. Temperature, it is always positive. Temperature can never be negative. It is in the Kelvin, right? But you know that water expands on freezing. The specific volume of ice, a specific volume of ice is more than a specific volume of liquid water. Okay. So this Vf minus Vs, this is negative. Okay. So this H is positive, T is positive, but this term is negative. Okay. So dP by dt at saturation. So this the slope of this line has to be negative. Why? Because Vf minus Vs, this thing is negative. Okay. Because water expands on freezing, but most of the substance they will not expand on freezing. Okay, they will expand on melting. But this water has some uh, interesting unique property that it expands on freezing. Okay, why it happens so? Because it has something to do with its structure, crystalline structure.
Yeah.
Water,
Yes.
egg, water, has some specific crystalline structure in the form of ice. Okay, so in the liquid state, it is just H2O molecules. They occupy the space efficiently. But in case of crystalline structure, there are some voids. Okay. Anyways,
Okay. Okay.
so
Sir,
yes, so this
can I ask a doubt?
yes, sure.
So if water between 0 to 4 degrees centigrade,
Water between 0 to 4 degrees centigrade.
yeah. So in that range, it will be that specific volume will be going on increasing. No? I think that to
Oh,
4
at four
degree
degree,
only.
see, at zero, at 4 degree, it is liquid, and 0 degree,
Yeah.
let us say it is solid. So
Yeah.
if you go from 4 degree to 0 degree, then yes, it is increasing. Specific volume is increasing.
Specific volume will be increased. So maximum density, I have learned that it is at 4 degrees centigrade.
So
So
maximum density
further,
will be exactly at the point where it is just melt. I mean, liquid, saturated liquid.
okay, but somewhere I have read like 4 degrees centigrade, water at 4 degrees centigrade has maximum density also.
Okay, it might happen. I'm not sure about that data. So I should check that.
Okay, okay. So one point was maybe later also you can clarify.
Mhm.
Like if you are, if suppose water is at 2 degrees centigrade, you have water at 2 degrees centigrade. If you are increasing the pressure, uh, temperature will decrease. On compression, temperature will decrease. Can
See,
that be proven?
water has some very peculiar properties. So for water also we had some diagrams in the that book. So if you go through those diagrams, I think then it will be clear. For water also we had certain diagram, no?
Okay.
Mhm. So for water, we have the diagram on the right hand side, and for other liquids, we have this on left hand side. So it has little different. It is little different. So here it is melting at this point, okay, on this line. Hello.
Yes, sir.
So water has some peculiar, I mean, properties. So is if we try to interpret on the basis of our general discussion, then we can get in trouble. So I can check your question. Maybe I can discuss that in next session. So what I have to check?
Okay, sir.
So one thing I have to check the density of water at 0 degrees Celsius and 4 degrees Celsius, and effect of pressure. Okay, these things, no?
on temperature. Yeah. Effect of pressure on temperature. Yeah.
Saturation temperature, you mean? If you mean only the saturation temperature, how the melting point will change with pressure, that can be explained from this diagram itself.
Yeah, but I think I'm asking the other, not the saturation.
Other.
Yeah.
If it is not saturated, if it is
Yeah, if
not
it is not
saturated, if it is not saturated, then we'll need another property, no? Because during saturation only the temperature is the function of pressure and the pressure is the function of temperature. If it is not saturation, then pressure and temperature will be function of each other, but also some other quantity.
Yeah, volume may be changing. That is also okay. No?
Volume may be changing. So one
Yeah.
thing we'll have to keep constant, no? One thing we'll have to keep constant, then we will say, okay, that particular quantity another quantity I'm keeping constant. Then this first variable I am changing, but the second variable I am
Yeah,
keeping constant.
temperature.
And what will happen on the
Okay,
dependent variable? Huh?
Okay.
Right, you got the point, no?
Yeah, I got it. Yes.
But the saturation pressure and temperature that you can explain from this diagram itself. If you increase the pressure, then the saturation temperature will decrease.
Okay, sir. Okay. Actually, the question was, if you have to keep the temperature constant on compression, why heat has to come into the system? That was the question actually.
Okay.
So first I assumed if temperature is not constant, what will happen? Then why how heat has to flow? That way I thought that.
If you want to keep volume constant,
If you want to keep temperature constant
if you want to keep temperature constant, okay,
and you're increasing the pressure.
and you are increasing the pressure.
Yeah, I read it has to come into the system because temperature will try to reduce. So to compensate that, it has to come into the system.
If you want to keep the temperature constant,
Yeah.
and you are increasing pressure,
Yeah.
then why we have to
Heat has to come into the system.
heat has come into the system.
Yeah. Otherwise, T will decrease. That is what they are saying. So from there only, my doubt has come why T has to decrease.
And it was in the specific context of water at these
Yeah,
unique
especially
conditions.
yes, water between 0 degree and 4 degree centigrade.
Okay, water between 0 degree and 4 degrees Celsius. That I think I should check the properties, what is happening out there. Okay.
Okay.
So we'll discuss that in next session. I have noted that. Okay.
Okay, sir.
So let's quickly discuss the remaining problems. Otherwise, today also we will not able to finish this. The thermodynamic phenomena which describes a pure substance such as water or bismuth that expands upon freezing and melts under applied pressure, then freeze again when the pressure is released. So this is called what? Sublimation, regelination, vaporization, or critical point transition. So this is called
Regulation.
regelination. It is saying that water near the normal melting point, 273 degrees Celsius, normal is at the atmospheric pressure. The specific volume of the liquid is this specific volume is given. The solid phase volume, specific volume is also given. The enthalpy of fusion is given. Using the small order approximation of Clapeyron equation, calculate the exact temperature change delta T when the pressure is increased by this.
Yeah.
So this we can calculate.
Yeah.
Okay. The absolute temperature of triple point of water is this. Is slightly But then its normal melting point temperature.
Higher. It's higher, slightly higher.
Triple point. So this is triple point and melting line is this one. So triple point is higher. Triple point is on that side. Because of negative slope of its fusion curve.
Yeah.
The Clausius-Clapeyron equation is an exact thermodynamic equation that accurately predicts the phase boundaries of all pure substances from triple point up to the critical point. This is false.
Okay.
Because it is Clausius-Clapeyron. Huh? So in Clausius-Clapeyron, we had certain assumptions. There are certain assumptions. Right? Those assumptions are not always valid. Okay.
Okay.
It is saying triple point to critical point. So one of the most important assumption was that specific volume of gas is very, very higher as compared to specific volume of liquid. But near the critical point, this is not valid, right?
Okay.
Question number 17. It is saying that state two specific physical and mathematical approximations that must be applied to the exact Clapeyron equation to derive the simplified Clapeyron equation. So one was this one only. Vg has to be very, very greater than VL. Okay. Another one was that at low pressure, ideal gas.
Approximation.
What else? Third one was that we assume that latent heat of uh, vaporization
Hmm.
is
Almost constant.
very small. No, it's approximately
Change.
constant.
Yeah.
I'm writing full thing so that those who didn't join, they can understand what we did. For very small changes. Okay, so these assumptions.
Okay.
By rearranging the Clausius-Clapeyron equation, the slope of the natural logarithmic of the saturation pressure with respect to temperature, this thing equates to what? Clausius-Clapeyron equation.
Yeah,
Where
that is 1 by P ln of P.
1 by P?
Ln of P can be written as d by dt of ln P.
What are you saying? LNP?
Sir, I'm saying 1 by P
1 by
1
P?
by P dp by dt. By
dp
P
by
dp by
dt.
dt
Uh-huh.
can be written as d
Can
by
be written
dt
as
of ln P.
dt by.
No, sir, that can be written as d by dt of ln B.
Your voice is not very clear. This can be written as
It can be written as d by dt of ln P. D by dt of ln P.
d by dt of
ln P.
LNP like this.
Yeah. dp is not required. Exactly. Yeah, exactly.
Mhm. So can this be written? I don't know. You need to check. What was
Yeah,
Clausius Clapeyron?
because P is a
So
function of t, no?
P is the
So I
function of
can
t.
write,
Yes.
so I can write like 1 by P into dp by dt.
Mhm.
Simple differential.
Right. Right. So which answers? Which option should be correct one?
So into P also may come Clapeyron. Then it may be that ideal gas approximation also can be written. So we have to relate between PV RT also. We have to write
Okay,
that equation.
let us write the Clausius-Clapeyron equation first.
Yeah, yeah, yeah.
dp by dt at saturation temperature is equal to what? Is P. I'm not writing the final step. I am starting writing with here
Okay.
from this RT square. Okay.
Okay.
This is after using the ideal gas equation, right?
Okay.
Actually, in the Clausius equation, this dp by dt was what? dp by dt in general in the Clapeyron equation, it was what? It was hfg divided by t times v fg. Okay. So h by t is still there. V fg was v fg we made equal to vg because vg was very higher as compared to vf. Then we use the ideal gas equation.
Yeah.
This
Now I
is
think.
equal to
Yeah.
okay.
Now I
Now we
think
can divide both.
P.
Now we can divide both side by p. So we can bring p on another side. Okay.
Okay, sir.
And t on another side. So dp by dt and 1p. Okay, so this p we are bringing that side. So h fg by r t square. Okay.
Okay.
So now what it is asking. 1 by p dp by dt is mathematically identical to, but where is the ln term and how this ln is coming?
ln is already in the 1 by P.
ln is already there in 1 by p.
Yeah. So 1 by P dp by dt only we have to find out.
Okay.
Our objective is to find out 1 by P dp by dt.
So this is now this only, no?
Yeah, that is what I also feel. Yeah.
So
That
option
only.
B should be. Okay.
Yeah.
Okay. 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 So you started from here, no? 1 by
Yes.
p times dp by dt. That should be equal to dt by dt of ln p. Oh, okay. 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 So there's no doubt in the question, huh?
Yeah, no doubt, sir. That is okay.
Okay, question number 19. It's saying like, unlike the fusion curve, the entropy of transition from a solid directly to a vapor during sublimation is always, I don't know, which mathematically guarantees that a sublimation curve will always exhibit a positive slope on the phase diagram. Yes, it is correct. I mean, on the phase diagram, PT phase diagram, the sublimation curve has always positive slope. But the entropy of transition from a solid directly to vapor is entropy change from solid to vapor. This should be equal to enthalpy change from solid to vapor divided by temperature. So this temperature is positive and this enthalpy is also positive. This should also be positive.
Yeah.
Next question. In computational thermodynamics, the saturation pressure temperature curve is often represented analytically as ln P saturation is equal to A plus BT plus C ln T plus DT. These ABC, all these are some constant. By differentiating this empirical equation with respect to T and applying the rearranged Clausius-Clapeyron equation, derive the explicit polynomial expression for the enthalpy of vaporization. plus dt. It is saying that by differentiating with this empirical equation with respect to t. So we have to differentiate this equation with respect to t. So this will be 0 plus b by t square minus b by t square plus c. And what is the differentiation of ln by t? No, plus d. Correct?
Yeah, correct.
And okay, so differentiation हो गया. Derive the explicit polynomial expression for the enthalpy of vaporization. So I think this we have discussed in the previous question. What was that? This was d by dt of ln p. D by dt of ln p saturation was what? D by dt of ln saturation p. This was exactly this thing, no? Na? D
Yes,
by
sir.
dt of ln p was 1 by p dp by dt, and this thing was this h by rt square. So this is h by rt square. Okay, and this thing is just the differentiation that we have just written, b by t square plus c by t plus d. And what it is asking, derive the explicit polynomial expression for the enthalpy. So HFG. So HFG can be easily written. HFG will be equal to R T square. So minus B and R T square will be cancelled out plus CR and 1T will be there plus D R T square. Okay. Fine.
Okay, okay.
Okay. So this is expression for enthalpy. Okay. So this was the last question. Okay.
Yeah, yeah. Yes, sir.
So I have noted your points that we will discuss in the next session. If you have any other doubt, that can also be discussed in the next session.
Sure, sir.
And regarding this, these recordings of previous session is there, and also this PDF I will upload again anyway. Okay, so you can
I
go through
yeah, I
how
will go
we
through.
use this Jacobians and all. So things will be clear. Okay, so thank you for joining. We'll meet in the next
Uh,
session.
sir, actually, we are celebrating Onam festival in Kerala this week.
This week.
Like,
Oh,
yeah. Are you aware of Onam festival?
yeah, I am aware. So
Yes. So
happy,
happy Onam to you.
happy Onam, happy Raksha Bandhan. A lot of festivals are there in this week, no?
Yeah, 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 yeah.
Okay, so enjoy the festival. Huh? We will meet. So by the next week, can we meet, or the holidays will be still there on the next Tuesday?
No problem. We will meet. I don't have any problem.
Okay,
It will be over. This week it will be over. Okay.
okay, 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 okay. Thank you. Happy Onam.
Happy.